If aliens are out there, why are they not here? That is the question people usually ask. But notice something strange about it. The question sounds simple only because we say it too fast. We put the whole galaxy into one sentence. We put life, intelligence, machines, survival, distance, time, and luck into one little complaint. Where is everybody? It is a wonderful question. I like it because a child can ask it, and a physicist cannot easily escape it. But if we are going to be honest, we should not begin with flying saucers. We should not begin with fear. We should not even begin with belief. We should begin with a bill. Because if another civilization wants to cross from one star to another, the universe does not ask whether it is curious. It asks whether it can pay. Now, that may sound cold. But physics is often cold in the beginning. Then, if you stay with it long enough, it becomes more interesting than imagination. Look at the Milky Way. The first feeling is abundance. Stars everywhere. Hundreds of billions of them. Planets around, many of them. Chemistry scattered through the dark. Carbon, water, energy, time. A person looks at that and says, surely Earth cannot be the only place where matter woke up and started asking questions. And maybe that person is right. I do not know. Nobody knows. That is the first honest sentence. But there is a trap inside the word alone. Alone may mean no life anywhere else. Or it may mean something much narrower. It may mean no one close enough. No one old enough. No one technological enough. No one noisy enough. No one arriving during the tiny little moment when we happen to be watching the sky. Those are not the same idea. They feel the same emotionally, but physically, they are different. And physics is very strict about differences that ordinary language hides. So, before we say, they should be here by now, we have to slow down and unpack the sentence. Life has to begin somewhere else. Fine. Then it has to survive. Then some of it has to become intelligent. Then intelligence has to become technological. Then technology has to last. Then that technology has to care about space. Then it has to build machines that can cross interstellar distances. And then those machines have to survive radiation, dust, cold, heat, navigation errors, mechanical failure, and time. Then, after all that, they have to arrive near Earth while human beings have telescopes, radios, cameras, and enough impatience to ask why nobody has knocked on the door yet. When you say it slowly, the question changes shape. Let us take only the distance. Not all the difficulty, just the distance. The nearest star system is a little over 4 light-years away. People say that word, only, as if it helps. Only 4 light-years. But a light-year is not a poetic unit. It is a brutal unit. It is the distance light travels in 1 year, and light is the fastest messenger nature allows. About 300,000 kilometers every second. Not every hour. Not every minute. Every second. So when we say 4 light-years, we are saying that even light needs more than 4 years to cross the gap. And that is the nearest star, not the average star, not the most promising star, not the one with a civilization politely waiting to send us a signal. The nearest one. Here is where the imagination cheats. We are used to maps. You put your finger on one place, move it a little, and now you are across an ocean. A centimeter becomes 1,000 kilometers. That is useful for paper. But space is not paper. Space is not an empty background with dots printed on it. Space is cost. It asks how much energy you have. It asks how long your machine can keep working. It asks how well you can aim. It asks how you protect your spacecraft from dust hitting like bullets, from radiation slowly damaging electronics, from the simple fact that a journey lasting decades or centuries is not a journey in the human sense anymore. It becomes a problem in survival. And there is one little detail people often forget. When you arrive, how do you stop? That sounds almost funny. But it is not. If a spacecraft goes racing past a star at enormous speed, it has not arrived. It has missed very impressively. To visit a system, you must not only speed up, you must slow down. That means more energy, more engineering, more mass, more planning. Science fiction often shows the ship appearing near a planet as if the hard part was getting there. But the hard part is not just crossing the ocean. It is crossing the ocean, finding one island in the dark, surviving the storm, and then stopping before you smash into the shore or fly past it forever. So when we ask why aliens have not arrived, we should be careful with the picture in our heads. Do not picture a quiet road with no cars. That picture is too small. Picture islands separated by oceans so large that even light needs years, centuries, or thousands of years to move between them. Then give every island its own accidents. Biology, climate, extinction, politics, economics, curiosity, fear, bad timing, simple indifference. A civilization might look at the stars, understand them very well, and still decide not to go. Or it may try and fail. Or it may send probes so small, so quiet, so old, or so unlike what we expect that we would not recognize them. Or it may have lived, looked upward, built wonderful instruments, and disappeared before the first human ancestor shaped a stone tool. That last possibility bothers people, because it makes the universe feel unfair. But the universe does not arrange its schedule for us. We have been technological for an absurdly short time. If another civilization sent a signal 10,000 years ago and then stopped, we would have missed it. If one begins sending 10,000 years from now, we are early. If one sends in a narrow beam that never crosses Earth, we are blind to it. Silence is not a simple thing. Silence is not the same as emptiness. If you sit in a dark room and hear no music, you cannot conclude that no one in the city owns a violin. You can only say that no violin is close enough, loud enough, aimed enough, and playing at the right moment for your ear to catch it. I am always a little cautious with analogies, because they can make hard things feel solved when they are not solved. But this one is useful, because it keeps the logic clean. Detection is not existence. Not detecting something does not automatically mean it does not exist. Sometimes it means your instrument is too weak. Sometimes it means you looked at the wrong time. Sometimes it means the thing is real but quiet. Sometimes it means your expectation was wrong. We imagine aliens as loud, expanding, broadcasting, arriving, building visible structures, leaving obvious signatures. But why should the universe obey our imagination? A mind very different from ours may not behave like a human empire with rockets. So I would reshape the question. Not, where are the aliens? As if the answer must be either they exist or they do not. A better question is this. How many physical gates have to open before another intelligence becomes visible to us? First, a planet must be suitable enough. Then chemistry must become biology. Then biology must produce minds. Then minds must produce tools. Then tools must produce astronomy. Then astronomy must become engineering. Then engineering must defeat distance, time, energy, failure, and survival. Then, after all of that, the result must cross our little patch of sky during the brief period when we know how to look. When you say it that way, the silence becomes different. It is still mysterious, maybe even more mysterious. But it is not a cartoon mystery anymore. It is not simply, why has no one visited? It becomes, which part of the chain is rare? Is life rare? Is intelligence rare? Is technology unstable? Is interstellar travel too expensive? Are civilizations quiet? Are they too far away? Are we too early? Are we too late? Or is the galaxy full of things we have not yet learned how to recognize? I do not know the answer, but I trust the question more when it is built this way. So no, the silence above us should not be used as a cheap answer. It should not make us smug. It should not make us hopeless. It should make us careful. The stars are far apart. Light has a speed limit. Energy is not free. Machines break. Living things are fragile. And civilizations do not get a guarantee of lasting forever. That is not an argument against aliens. It is the ground we have to stand on before the question becomes honest. Maybe there is no one. Maybe there are many. Maybe they are listening too. Maybe they tried and failed. Maybe arrival is the rarest step of all, and that is why I would not begin this story with a spaceship in the sky. I would begin with scale. I would begin with the uncomfortable size of the galaxy, the finite speed of light, the cost of motion, and the smallness of our listening window. Because in physics, the first answer to a big question is often not yes or no. It is slower than that. It is more demanding than that. It says, before we decide what the universe means, let us measure what the question costs. Okay, so before we say aliens should have arrived already, let us slow down for a moment. Not because the question is silly. It is not silly at all. It is one of the best questions a curious mind can ask. But there is a trap inside it. The trap is the word arrived. It sounds simple. It sounds like moving from one place to another. You look at a map, you see two dots, you draw a line, and the problem feels almost solved. But the universe does not travel by lines on paper. A finger can cross a star map in half a second. A spacecraft does not get that privilege. In physics, distance is not just empty space waiting to be crossed. Distance becomes time. Distance becomes energy. Distance becomes heat, dust, radiation, failure, delay, and uncertainty. Once you count those things, the question changes. It is no longer simply, why are they not here? It becomes, what would it actually cost to get here at all? Take the nearest star system, just over 4 light years away. People hear nearest and feel comforted. Nearest sounds friendly. It sounds like a neighbor across the road. But a light year is already a brutal unit. It is not a year of waiting. It is the distance light itself travels in 1 year. And light is not slow. Light crosses nearly 300,000 kilometers every second. Say that slowly, every second. In the time it takes you to blink, light has gone farther than any airplane could dream of going. Then stretch that motion across a year. Then multiply it by more than 4. That is our nearest stellar neighbor. Near only means near compared with the rest of the galaxy. It does not mean near for engines, metals, fuel, computers, or living bodies. Now, the obvious answer is, fine, make the spacecraft faster. That is the first instinct. It is also where the bill begins. Suppose a probe moves at 1% of the speed of light. 1% sounds small. It sounds almost modest, like we are being conservative. But 1% of light speed is about 3,000 kilometers per second. That is not airplane speed. That is not bullet speed. That is a machine moving so fast that ordinary comparisons start to fail. And even then, even at that absurd speed by human standards, the nearest star still takes more than 400 years to reach. 400 years for the nearest one. Not the interesting one far across the galaxy. Not the perfect target. The nearest one. And that assumes the machine keeps working, keeps navigating, keeps power, keeps its structure, and still has something useful to do when it arrives. But even that picture is too generous, because travel is not just going fast. You also have to arrive. That sounds obvious, but it is the part maps hide. A map shows departure and destination. It does not show braking. If you throw a probe across interstellar space and it screams through another star system at enormous speed, that may be a flyby. It may collect something. It may take a few measurements. But it has not arrived in the deeper sense. To arrive, it must slow down. And slowing down is not free. The universe does not say, "You already paid to accelerate, so I will let you stop politely." No. Motion carries energy. If you want to remove that motion, you must deal with that energy again. Carry fuel, carry a sail, use radiation, use magnetic fields, use gravity, use some clever trick, fine. But every trick still has physics inside it. Every solution has mass, timing, geometry, failure points, and engineering consequences. And then there is the little matter of not being destroyed on the way. I say little matter because sometimes it really is little. A grain of dust, for example. At ordinary speed, a dust grain is nothing. You wipe it from a table. You never think about it again. But at interstellar speed, that same tiny grain becomes a serious collision. The spacecraft does not experience space as empty. It experiences rare matter as projectiles. So now you need shielding. The shield has mass. And mass is never innocent in spaceflight. If you add more mass, you must push more mass. If you must push more mass, you need more energy. If you need more energy, your system grows. And when the system grows, the number of things that can fail grows with it. Notice what happened there. We did not meet one giant wall. We met a staircase. Dust leads to shielding. Shielding leads to mass. Mass leads to energy. Energy leads to infrastructure. Infrastructure leads to complexity. That is how physics often says no. Not with drama. With accounting. Radiation adds another line to the bill. Interstellar space is not a soft black emptiness. It has charged particles, cosmic rays, magnetic fields, stellar winds, and high-energy events spread across enormous time. A living crew would need protection, repair, air, water, food, heat control, waste handling, medicine, and probably a whole social world just to remain sane. A machine is easier, yes. Much easier. But machines are not magic stones. Electronics degrade. Materials fatigue. Power systems decay. Tiny errors accumulate when nobody can put a hand on the machine and fix it. An advanced civilization might solve many of these problems. We should be fair about that. But solving a problem is not the same as erasing the cost. It only means the cost has been paid somewhere else. Communication is even stranger, because it feels invisible until you need it. Suppose a probe reaches a star 4 light-years away and sends back a message. That message still takes more than 4 years to return. If the target is 100 light-years away, the reply takes a century. There is no live steering in the ordinary sense. No quick correction. No conversation with home. The probe must think for itself, or at least act for itself, under conditions its makers may only have guessed at. And if something goes wrong, the news comes back long after the moment when help would have mattered. Interstellar travel is not only transportation, it is delayed knowledge. So I would be careful with the sentence, if aliens exist, they should be here. There are too many hidden steps inside that little word, should. Life has to appear. Intelligence has to develop. Technology has to move in the direction of star travel. The civilization has to decide that crossing light years is worth the cost. Then its machines must survive speed, dust, radiation, time, braking, navigation, and silence. And even after all of that, they must choose this ordinary star, this ordinary planet, during the very thin slice of cosmic history when we are able to notice. When you say it plainly, the silence is still mysterious. But it is not a childish mystery. It is not just, where is everybody? It is, under what physical conditions could anybody cross the dark and arrive in a way we could actually recognize? One thing we should get straight right away. Distance is not the whole problem. Distance is the first shock. You look at the nearest star, you hear 4 light-years, and already your mind begins to stretch. But then physics comes in and says, wait a moment. Do not only ask how far it is. Ask what it costs to move something there. Because a starship is not a thought. It is not a line drawn on a map. It is matter. It has mass. And if matter is sitting here, and you want it to be moving very fast over there, you have to pay for that motion with energy. Now that sounds simple. Almost too simple. Push the thing, give it speed, send it away. But the trap is hidden in the word speed. At ordinary speeds, the energy of motion does not grow politely. It grows with the square of speed. Say that slowly, because it is where many science fiction pictures become a little too soft. Double the speed, and the energy is not doubled. It becomes 4 times larger. Make the speed 10 times larger, and now the energy is 100 times larger. And this is before the engine has made heat. Before the tank has mass. Before the shield has to protect anything. Before one tiny bolt breaks at the wrong time. Let me make it less abstract. Suppose a probe moves at 1% of the speed of light. 1% sounds modest, doesn't it? It sounds like a careful number. Not reckless. Not wild. But 1% of light speed is about 3,000 kilometers every second. At that speed, the spacecraft is not merely traveling through space. It is carrying a violent amount of energy just by moving. And now imagine a dust grain in its path. Not a rock. Not an asteroid. Just a small grain, the kind you would ignore on your desk. At that speed, it is no longer a harmless speck. It is a physical event. The spacecraft hits it, and the universe does not care how hopeful the mission was. The energy has to go somewhere, so you add shielding. Of course you do. A sensible engineer says, protect the craft. But the shield has mass. Then the craft is heavier. Now it needs more energy to reach the same speed. More energy may require more fuel, or a bigger sail, or a larger beam, or stronger structure. And each of those answers brings another problem into the room. This is the part people often skip. Interstellar travel is not one big problem sitting alone. It is a chain of problems holding hands. You solve one, and another one quietly gets heavier. Rockets make this especially painful. A rocket usually has to carry much of its own answer with it. The fuel is not weightless. The tank is not weightless. The engine is not weightless. Even the frame, the pipes, the pumps, the insulation, the parts you do not put on posters, all of it must be accelerated. So you add fuel to go faster. But that fuel makes the vehicle heavier. Then you need more fuel to push the fuel. After a while, you are not just building a machine. You are arguing with arithmetic. And arithmetic is a very patient opponent. It does not get tired. It does not become impressed. That is why people bring up nuclear engines, fusion drives, antimatter, laser sails, magnetic sails, and ships that move slowly for generations. These ideas are not silly just because they are hard. Some of them are serious attempts to escape the worst parts of the rocket problem. Nuclear energy gives far more energy per kilogram than chemical fuel. Fusion would be better still, if you could make it behave as an engine and not just as a star in a bottle. Antimatter sounds almost perfect on paper because its energy density is enormous. But then you have to make it, store it, control it, and stop it from destroying the thing that is supposed to use it. A light sail is clever in a different way. It says, "Do not carry the fuel. Leave the pushing system at home." But then home must build a beam powerful enough to push a craft across astronomical distance, aim it with absurd precision, keep the sail stable, and somehow solve the problem of stopping later. So the cost has not vanished. It has moved. Now, I want to be fair to the imagination here. Physics does not say that every journey between stars is forbidden. A slow probe is not impossible. A patient civilization might send machines outward. A very old society might think in centuries the way we think in decades. So the honest answer is not, no one can ever go. That is too easy, and science should not be lazy in either direction. The better answer is this. Physics removes the cheap version. You do not get the stars for the cost of an airplane ticket. You do not get galactic travel simply because intelligence appears. Wanting to arrive is not propulsion. Curiosity is not a heat shield. Hope is not a braking system, and if you try to make the craft faster and faster, relativity steps in. At first, ordinary motion feels familiar. More speed needs more energy. Fine. But as the speed becomes a serious fraction of light speed, the old simple picture breaks. The energy required rises more severely. A massive object can get closer and closer to light speed, but it cannot reach it. This is not because the engine is poorly designed. It is because space-time has rules built into it. Light speed is not just a fast number. It is tied to cause and effect. It is part of how space and time talk to each other. So when someone says maybe aliens just go faster than light, I would not laugh. I would stop for a second. Because that is not merely asking for a better engine. It is asking for a new relationship between energy, causality, space, and time. There are mathematical ideas that sound like doors. Warp drives. Wormholes. Shortcuts through space-time. They are interesting. They are worth thinking about. But a mathematical possibility is not automatically a machine in a hangar. Sometimes the idea needs matter we do not know how to obtain. Sometimes it needs stability we do not know how to maintain. Sometimes causality itself seems to stand in the doorway and say, "No, be careful." So now the alien question changes shape. It is not only, are they out there? It is, can they afford arrival? Can they command enough energy? Can they survive dust, radiation, heat, time, failure, and breaking? Can their civilization care about one mission long enough for the mission to matter? And after all of that, would we even notice them? The sky may be quiet for many reasons. Maybe travelers are rare. Maybe probes are slow. Maybe communication is easier than visiting. Maybe the galaxy teaches every intelligent species the same cold lesson. The stars are not forbidden, but they are not nearby in any human sense. And when I hear the word arrival, I hear the whole bill arriving with it. The problem gets bigger than engines, bigger than fuel, bigger than whether a machine can survive a trip between stars. Suppose somewhere out there a civilization really does solve the engineering. It learns how to shield a probe from dust, how to guide it for centuries, how to store energy, how to be patient in a way human beings are not very good at imagining. Fine. Let us give them all of that. The galaxy still may not become loud, because the galaxy is not just wide, it is old. And old things have a strange trick. They can contain many events that never overlap. We usually picture aliens as neighbors. Someone over there, looking up tonight, while we look up tonight. That is a very human picture, because our minds live in the present moment. We make a cup of coffee now. We hear a sound now. We ask the sky a question now. But the Milky Way does not run on human time. It has been making stars and planets for billions of years. Earth needed more than 4 billion years to produce one species that could build radio transmitters, and then wonder why nobody is calling. So if another civilization appeared 1 million years before us, that sounds almost close on a galactic clock. Just a little offset. But for technology, 1 million years is enormous. It is longer than all recorded human history by so much that the comparison nearly loses meaning. So the question can not only be, are they there? The sharper question is, when are they there? A world may have life, and life may become complex, and complexity may stumble into intelligence, and intelligence may eventually find tools. But the technological part may be brief, maybe 10,000 years, maybe 100,000, maybe much less. I do not know. Nobody knows. But that ignorance is not a small detail. It is the whole difficulty. Two civilizations can both be real, both clever, both looking outward, and still miss each other completely. One sends before the other can receive. One listens after the other has gone quiet. Then the galaxy is not empty. It is out of rhythm. That is easy to say. But slow down and feel what it means. Space separates worlds. Yes. But time separates histories. A signal from a civilization 1,000 light years away needs 1,000 years to reach us, even if it travels at the fastest speed nature allows. If we answer, our reply needs another 1,000 years to go back. That is not really a conversation. It is closer to finding a message in a bottle, except the ocean is the galaxy, and the person who wrote the message may no longer exist. Communication is cheaper than travel. Yes, but it is still trapped inside timing. Light is fast for us, but not fast enough to make a galaxy feel small, and then there is life itself. which is where we should be careful. We have one example, one planet, one history. That is a terrible sample size, but it is the sample we can touch. On Earth, simple life appeared early, but technological intelligence appeared very late. That does not prove intelligence is rare everywhere. I would not claim that. It only warns us not to treat it as automatic. Bacteria are not failed astronauts. They are successful life. A planet could be alive for 3 billion years, with oceans full of chemistry, strange forests, thick atmospheres changed by living things, and still never build one telescope, never send one radio pulse, never scratch its name into the dark. Even intelligence is not the same as technology. That is another place where we fool ourselves, because we look at our own path and quietly assume it is the normal path. Dolphins are intelligent. Crows solve problems. Octopuses are astonishing little engineers in soft bodies, but they do not smelt metals. They do not build radio dishes. They do not launch probes. Technology needs a peculiar chain of conditions, something like hands, some path to controlled energy, useful materials, stable environments, memory passed from one generation to the next. A clever creature under an ocean may understand its world beautifully, but never discover fire. Not because it is stupid, because physics has not given it the same doorway. So maybe the silence is not one great wall. Maybe it is many little doors. A planet has to keep its air, keep its water, avoid too many catastrophic resets, stay friendly long enough for life to experiment. Then life has to become complex. Complexity has to become intelligent. Intelligence has to become technological. And technology has to survive its own power. That last part sounds moral, but it is physical too. Energy systems, weapons, climate, food, ecosystems, social stability. A technological species becomes dangerous before it becomes wise. I do not mean that as a sermon. I mean it as a risk built into capability. Now, put those pieces together. A galaxy may have many living worlds, but only a few technological ones. Those technological windows may be scattered across billions of years, like sparks appearing in different rooms of an enormous dark house. Some burn early, some burn late, some never become bright enough to see from outside. Add the cost of interstellar travel. Add the difficulty of detection. Add the possibility that many civilizations simply choose to stay near home, and the silence becomes less strange, not solved, but less naive. A quiet galaxy does not automatically mean a dead galaxy. It may mean that the road from chemistry to starflight is narrow, fragile, and badly timed. There is also a hidden assumption in the sentence: they would have colonized the galaxy by now. It assumes desire. It assumes expansion is natural for every mind. It assumes civilizations behave like fire spreading through dry grass. But a mind is not fire. A civilization might decide expansion is dangerous, wasteful, unstable, or simply not worth the cost. It might build close to its own star, reduce its energy signature, send narrow beams instead of loud broadcasts, or become very good at being unnoticed. Or maybe it just does not care about us. That is not an insult. It is a reasonable possibility. Earth matters intensely to us because we are here. To a distant intelligence, It may be one small wet rock around one ordinary star. And from our side, detection is brutal. We do not watch the whole galaxy all the time, in every frequency, with every possible instrument. We sample, we guess, we point somewhere and hope the universe is speaking in a way we know how to hear. If a signal is narrow, we may not be in the beam. If it is brief, we may look too late. If it uses a method we have not imagined, we may look straight at it and see nothing. Searching the sky is not like opening a door. It is like trying to hear one careful whisper during a storm, while not knowing the language, the direction, or the hour. That is why the Fermi question still matters. It does not prove we are alone. It never proved that. It does something more useful. It forces us to stop using hope as a mechanism. If life is common, what makes it visible? If intelligence is common, what makes it technological? If technology is common, what makes it interstellar? And if interstellar machines are possible, what makes them detectable here? Now, the silence may not be empty. It may be telling us that existence, intelligence, communication, travel, and arrival are not the same thing. Once you separate them, the mystery becomes less like science fiction and more like physics. Timing matters, fragility matters, and distance is only one part of the dark. So now we can come back to the question, but I want to come back to it more carefully. If aliens are out there, why have they not arrived? It is a dangerous question because it tempts us to answer too quickly. We want one clean sentence. They do not exist. They are hiding. They are too far away. They destroyed themselves. They came here and we missed it. But I do not trust answers that become neat too fast. Nature is rarely that polite. A galaxy is not a room where someone either knocks on the door or does not. It is a vast physical system, full of distance, time, chemistry, accidents, energy costs, and limits we cannot talk away. The first thing to notice is that the question has many steps hidden inside it. Life has to appear. Then life has to become complex. Then some kind of intelligence has to appear. Then that intelligence has to make tools, survive itself, understand energy, build machines, and last long enough to look outward. And even after all that, it has to decide that crossing interstellar space is worth the price. That is not one problem. That is a staircase. And a staircase with many missing steps will still look like silence from far away. So I would be careful with both easy answers. I would not say, obviously we are alone. That runs beyond the evidence. But I would also not say, obviously the galaxy is crowded with visitors. That runs beyond the evidence too. What we can say is smaller, but stronger. We have no verified evidence of extraterrestrial visitors. We have no confirmed signal from another technological civilization. At the same time, we know the galaxy contains enormous numbers of stars and planets. We know the ingredients for chemistry are not special to Earth. And we know that on one small planet, matter did become alive, curious, and technological. That does not solve the question, but it makes the question serious. Now think about Earth, not as a miracle for a moment, just as a physical object. For most of its history, Earth was alive but quiet. Oceans were here. Cells were here. Evolution was working day after day with no audience. But if you were far away, looking for technology, you would have seen almost nothing. No radio towers. No radar beams. No spacecraft leaving the Sunday. No artificial lights on the night side. For billions of years, the most important things on this planet were happening without any announcement to the galaxy. That should slow us down. If another Earth exists, and we look during the wrong stretch of time, we may not see a dead world. We may see a living world before it has learned how to speak, and even our own speaking has barely begun. Our loud technological period is not ancient. It is a blink. A few generations of radio. A few decades of spacecraft moving beyond the familiar planets. A few moments, on a galactic clock, of instruments good enough to ask whether someone else is there. Imagine opening a window in a mountain valley for 1 second and then saying, "Nobody answered, therefore nobody lives anywhere in the mountains." Maybe that is true. But it is not a careful conclusion. Maybe someone spoke before the window opened. Maybe someone will speak after it closes. Maybe their voice is too faint. Maybe we are listening in the wrong direction. The point is not to force the analogy. The point is timing. In this problem, timing is not decoration. Timing is part of the experiment. So what should the silence make us feel? I do not think it should make us panic. I do not think it should make us proud either. It should make us careful. Careful with the difference between possibility and fact. Careful with the difference between no evidence and evidence of absence. Careful with the habit of turning mystery into a story that flatters us. The universe does not owe us visitors. It does not owe us a message. And it certainly does not owe us an answer during the short little interval in which our species has been able to listen. There is something useful in that uncertainty, though I know that sounds strange. Usually we want uncertainty to disappear. But in science, honest uncertainty is not emptiness. It tells you where the work is. The Fermi question points in many directions at once. How often do planets form? How often does chemistry become biology? How often does intelligence become technology? How long can technology remain stable without destroying itself or turning inward? How expensive is travel between stars, not in dreams, but in energy, heat, mass, and time? These are not campfire questions once you look closely. They are measurement questions, and this is where the silence becomes more interesting, not less. If life is rare, then Earth is precious in one way. If life is common but intelligence is rare, Earth is precious in another way. If intelligence appears often but civilizations are brief, then the problem becomes more serious and more personal. And if civilizations last, but do not travel much, then maybe the galaxy is not empty. Maybe it is simply not arranged for our convenience. Near is not the same as out there. Alive is not the same as technological. Technological is not the same as stable. Stable is not the same as expansionist. And capable is not the same as detectable by us, here, now. Break one link in that chain, and the sky can remain quiet. So I would end the question without pretending to know more than we know. The silence above us may be absence. It may be distance. It may be bad timing. It may be that arrival is rare even when life is not. But the question has already done something valuable. It forces us to stop treating the stars as decorations. They are real suns, with real planets, separated by real distances and real limits. And from this small planet, around this ordinary star, we have just begun to ask whether somewhere else, matter has also learned to wonder. That is a good question. Not because it has an easy answer, because it does not. And if physics teaches us anything, it is this. Reality is not required to match our first intuition. We have to measure it. We have to test it. And when we do not know, we should have the discipline to say so. That is not weakness. That is how a mind stays honest in front of a universe much larger than itself.